My topic is understanding SeaStore through profiling, and my name is Yingxin. I have been working on the Crimson project for years, and I'm mostly familiar with Crimson Messenger and SeaStore part, and I'm from Intel. So a little background. So the goal of the Crimson and also SeaStore is to use multiple CPUs effectively to drive the fast I/O from the modern hardware. And it uses share nothing design so that most of the mutics and the shared resources across core can be removed, and also designed as a run to completion to minimize the cross-core jumps and also the context switch overhead. And the goal is to make the performance scalable with cores, and the implementation is based on the SeaStore framework, which bridges the gap between the OS and hardware and the Crimson software to fulfill the design goals. And all the Crimson code are implemented on the SeaStore framework. And for the SeaStore, it aims to support multiple kind of devices, for example, SSDs, NAS, etc. And they have vastly different performance characters. Some are very good at sequential write, and some are very good at a random write. And HDD is is very cheap. That can serve as the code tier. So about profiling, the first step is to generate the workload. It may be from the librd client or Rados, or it can be from the store MBD that can generate the workload directly to the store. And the next step is to collect the metrics from the SeaStore framework, which needs to be implemented in the software layer. So the data can be collected, like, for example, every 60 seconds. And there will be a lot of data, so we need visualization to understand the relationship and of the collected data. And why do we need that? Why do we need that? Because the end performance is, if without the profiling, we can only have the performance from the client side and also from the operating system side, but they are not enough to diagnose synthetic issues from multiple problems at the same time. And we may also need to predict the trends of the performance and identify the potentials of from different implementations to understand whether we need to invest efforts and complexity to optimize them. And when introduce new features, we need to identify performance regressions, and that may also involve multiple issues at the same time. And we need to understand various test scenarios and their internal impacts to the SeaStore. And also we need to validate different features and fixes to make sure they are under the expectation. So this topic will be divided into 4 parts. The first part is the necessary SeaStore background to understand how we are doing profiling. And there are 5 different parts of profiling that will be included in this topic, and the real examples to understand how we are doing profiling with the optimizations, and the final part is the key takeaways. So this part may be there are some repeat from the previous topic, but I will go through them. So SeaStore basically implements the ObjectStore interface from the OSD. So it is the local storage backend for the OSD, which supports features like multi-level indexing from the collections to onodes, and also the key values in the onode, and to index the data by the offset for each onode. And all the onode must be ordered across the cluster. And OSD requires multiple operations that may operate on different onodes, collections, and key values to be transactional. Means they must be all successful or not successful when there's a power out. And it needs to support lightweight copy on write. And the example, there are multiple implementations to that ObjectStore interface. For example, MemStore, FileStore, BlueStore, and SeaStore is designed for the Crimson OSD. And the logical structure here is that all the data will be accessed from the single root block, and the collections and the onode and the second level index key value pairs and the data can all be indexed through these trees, which is consists the logical part of the SeaStore, and also there's a physical part of SeaStore which implements logical block address to a physical block address translation, and also the reversed translation from physical to logical. So there are basically 4 kinds of trees to index different kinds of data. And from the code level, the implementation is layered. So the bottom layer is the physical layer, which is responsible to manage physical blocks, which also is responsible to handle lower level features like garbage cleaning and handle transaction conflicts, and it also supports caching and journaling, and it encapsulates the complexities in the physical layer. So a logical layer only needs to be responsible to manage logical blocks, and with the transaction semantics to implement the essential features for the ObjectStore interface. And all of them are implemented based on the SeaStore. And the physical layer basically follows the log structured file system design, which includes journaling and cleaning. So all the user data will be appended to the journal head sequentially, and periodically the journal tail needs to be advanced and the journal to be trimmed so that when SeaStore is restarted, all the journal only needs to replay from the journal tail and rebuild the dirty blocks in the memory. And the data needs to be continuously reclaimed so that the journal head can be keep appended. And this comes to the important concepts that's related to profiling. So all the transactions are categorized into 4 sources: the read-only transactions, and the mutate transactions, that is to append the journal head, and the journal trimming transactions, and the space reclaim transactions. these transactions can be executed in parallel so that they can be conflict to each other, especially when a transaction wants to mutate a block that was read by other ongoing transactions. So when one of the transaction is submitted, the other conflicted transactions must fail and retry to preserve the correct transaction isolation level. And at the disk level, the writes are to the different write streams, or called the submitters. And there is only one inline submitter to append the data to the journal head, and there can be several out-of-line submitters that can write data independently outside the journal before the transaction is submitted. So that's basically the background to understand the profiling. So the very basic thing that profiling that we need to know is the write activities of the SeaStore. So these are overall profiling to understand the IOPS throughput, average write size of the SeaStore, and it can be further divided by the transaction types, the sources, so we can understand the write activities from different kinds of transactions. And also it can be divided by the low-level submitters with further useful metrics, including the IO depths of the transaction and how the small writes are coalesced into larger writes in batches, and the write fullness, because SeaStore needs to add paddings for 4KB in order to write to the block device. And the next part is the write amplification, which is very important to understand a storage system. It is calculated, the overall ratio is calculated by dividing the disk write by the client side write, and the analysis can be in a top-down fashion, so we can see how different layers, including the logical layer and the physical layer that was introduced before, that contributes to the overall write amplification ratio. And it can be further divided by the transaction types, and for each type of the transaction, it can be further categorized by the fresh data, delta data, and invalid data, etc., about their individual write amplifications. And it can also divide it by extent types, which means it is divided by different components. For example, the onode, the OMAP, and LBA, etc. And the next important factor to understand is the transaction conflicts, which can be calculated by dividing the invalid transactions by the actual committed transactions. It can also divide it by transaction types, and it can also be evaluated by actual wasted efforts, because a transaction may be a conflict very early or very late. So their read, mutate, and write efforts may be different. And we need to understand the conflict reason. So for example, where the conflict comes from, so which component it comes from, which comes to the extent type of the conflicting extent, and also the source pair of the conflicting transactions is also was to understand. And the next part is the garbage cleaning, which is the essential feature of the physical layer. So in SeaStore, the space was divided in segments, so they can be monitored. So the status of segments can be monitored. So we can understand how many of them are empty or open or closed by time, and the operations on the segments per second, and also the usage distribution of the segments to understand the data, how many data are live in the segments, and also the space ratio, as the space can be divided by the unused space and the space that was in journal, and the space that is reclaimable, which also includes the alive data and the unalive data that can be actually reclaimed. The user I/O will be can be blocked by a journal trim or space reclaim. So there are the graph to understand when these user transactions are blocked by which operation. And there are other useful monitors, for example, the CPU, which will include a very important part about the busy polling, because as we can understand how much CPU was used for busy polling and how much CPU was used for the actual workload. And this information is not available at the operating system level. And also the metrics, the monitor of the memory to understand the memory usage, and the cache monitor that can report the hit ratio by time, and also the cache sizes, and the tree metrics that will report the tree depths and the tree operations to the different kind of trees. And also there are metrics from SeaStore framework, including the number of tasks and pulls. Okay, so the next part is the real examples from the profiling to the optimizations. So the first issue we realized that is there is a huge write amplification from the onode-tree, which is about 1.5, and we realized that the static onode size is too large, so we implement a PR to minimize the onode size, and the profiling proves that the writes from onode is decreased by 5 times, but it doesn't show up in the end performance because it is hidden by inefficient GC and intensive conflicts, and at that time, because there are larger problems at that time. So we comes to try to address the transaction conflicts, and that is because the writes are not clustered by PGs. So that because the concurrent transactions will come from PGs, so we introduced a series PRs to introduce logical address hints to cluster allocations by the PG, and the profiling proves that the conflict ratio drops from 180% to only 5%. We see end performance improved by 100%. So it's very effective optimization. And the next issue is that we found out the out of line write padding is too huge. That takes 0.7 write amplification. And we found that we have split the already very small user writes into multiple out of line streams. So we decided not to split user writes to eliminate the unnecessary write overhead. But we still need a better way to split writes. And then it comes to the overall write padding. because the user writes are still too small for the 4KB blocks. So we designed the record submitter to coalesce small writes into larger ones that is effective to reduce the overall padding write amplification from 0.65 to around 0.2, and it also the record submitter also takes control of write IO depths, write fullness, and the write size to strike a balance between the latency and throughput. And we have applied it to all the write passes, including the out of line and the journaling pass, so that we can now divide and split the out of line writes with write coalescing. And the next part is garbage cleaning, and we noticed that the overhead from trim and reclaim are very huge, and that is because the trim and the reclaim are too regressive. So we tried to increase the journal size to delay a trim as late as possible, and also find a way to delay reclaim as late as possible. And the profiling proves that that strategy is effective, and it also benefits the conflict issue between trimming, cleaning transactions and user transactions, and that results in the conflicted write amplification drop from 2 to 0.25, with the end performance improved by 20%. But the cleaning strategy is still too coarse. So we've designed the generational GC with an improved segment selection policy. The goal is to form better bimodal segment utility distribution. And from the profiling, it is proved that before the generational GC, all the segments will end up with uniform utilization around 20% to 40%. And after that generational GC is implemented, half of the segments will have only 10% of utilization, and another half will be 50 to 90% of the utilization, which means that we only need we need to reclaim less alive data in order to release the same amount of segments, which also proved by the profiling that the trim and reclaim overhead are dropped, and with the end performance at the steady state has been improved by 10%, which is also workload dependent. So that's basically the examples from the profiling, and the last part is takeaways. So the first thing we learned is that the profiling is a larger part compared with the optimizations. We have introduced over 1,000 metrics with 28 PRs for profiling and tooling, and there are 15 PRs for the actual optimizations. And also the optimizations need to be profiling oriented to make sure the direction is correct, and also we won't introduce unnecessary complexities. And the profiling iterations needs to be involved in all the steps, including identify issue and identify the test scenario, and to reproduce the issue and root cause the issue, and also propose the solution and verify that the solution is actually effective. And the point 3 is that profiling needs to be balanced between the introduced overhead and the introduced complexity into the code. in order to get the necessary analysis steps, and there may be different goals for the profiling. So for the developments, we might need very detailed metrics to understand the features and the impacts. But if for the monitoring, we may not need so many of metrics with unnecessary overhead and complexity. And there are some useful reference, including the SeaStore framework introduction and the scripts to collect metric data and parse metric data. But these scripts can be out of date for some time because we are keeping changing code there. So it needs to be updated. And also the SeaStore code is there, and the design of log structured paper link is here. So that's all from me. Any questions?
I think we got a question in chat. Will Crimson OSD, will SeaStore be able to optimize themselves based on real-life workload performance characteristics? Automatic memory allocation, for example?
Well, I haven't think about that. So the current optimization are fixing very severe issues that because the implementation is still initial. So I think that may be a good direction if the original implementation is solid after that. Will it be possible to do tracing of client I/O based on the tags dataset? For example, to figure out what events caused by. I think it's possible, but yeah, but we need to figure out how to do that to connect the operations to the issues, because they are usually at different levels. So we need to find a way to connect them.